Okay, so the next talk will be from on one on the voice filter, and yeah, we're looking forward to it.
Okay, so hello everyone. My name is Chen Wang. I'm from the Google Speech team. Today I will introduce a system we developed named the VoiceFilter. This system separates the voice of the typed speaker by conditioning the spectrogram masking algorithm on the speaker embedded. Before we go to any technical details, I want to show a demo video.
This isn't part of your testing routine, is it? This isn't part of your testing routine, is it?
When I came up to touch my shoulder,
Be so
and
kind
looked
as
searchingly
to
down into my face for several
Here's
seconds.
the key of the door.
When I came up to touch my shoulder, and looked searchingly down into my face for several seconds.
Move it backwards and forwards until the bread is nicely covered, and turn it and toast the other side, and do not place it so near the fire that it blackens. Move it backwards and forwards until the bread is nicely covered, and turn it and toast the other side, and do not place it so near the fire that it blackens.
As per the Eucharist,
It's a case in 1,000, Christ.
Well, we have had
Mary
a
of my
vacation, and I'm willing to go to work
overflap.
again. Well, we have had a good vacation, and I'm willing to go to work again.
Okay, the demo is cool, so let's see how it works. The problem we are solving is known as the cocktail party problem. When multiple talkers are speaking, and you only want to listen to one person, that's easy for human, but difficult for machines. If there are multiple channels, like a human has 2 ears, multi-channel blind separation algorithms can be used. But many devices, like the mobile phone, only have one microphone. Then single-channel blind separation algorithms can be used. Let's look at an example. Here are 3 spectrograms. The first is a female voice, the second is a male voice, and the last is a mixed one. Let's listen to them. The first one is
Similar to
female.
an acoustic model.
The second one is a male voice.
What's the weather? Is it gonna rain?
The last one is when we mix them together.
Similar
What's the
to an
weather? Is
acoustic
it gonna
model.
rain?
Okay, so if we want to recover the male voice from the mixed one, intuitively we could use an eraser on the spectrogram to remove the harmonics of the female voice. In practice, this is doable, and we call that spectrogram masking. There are already lots of great work on single-channel blind separation, for example, the deep clustering, deep attractor network, and the permutation invariant training. But these are not really what we want, because in our cases, we really know whom to listen to. For example, if you have an Android phone or Google Home device, you can enable voice match, which will store a voice profile on the device. With this voice match, or with this voice profile, we are no longer blind. Here I will explain why blindness sucks. First, in blind separation, you don't know how many sources are there in the runtime. You may be doing great when the input has multiple sources, but you also don't want to mess up when the input is already single source. Second, blind separation usually has multiple outputs. You still need to pick the one you need, for example, using ASR. You can simply pick the loudest one from the outputs, or use an additional speaker verification step, but that's not a trivial task itself. Finally, permutation invariant training is usually very expensive. So with the proposed voice filter system, we can say goodbye to blindness. We make use of the speaker embedding, which can be acquired during user enrollment. This speaker embedding will condition the separation system to output the clean signals from the target speaker. Next, I will talk about our models. We basically have 2 models, and they are separately trained with different data sets. The speaker encoder model takes an utterance as input and outputs a speaker discriminative embedding. The voice filter model takes both a noisy spectrogram and the embedding as input, and outputs a mask. The speaker encoder is also known as the D-vector system. It's basically a multi-layer LSTM network. You can find more details in this paper. I also uploaded my lecture on this system to YouTube, so you could watch this video if you are interested. Basically, our D-vector system is a highly scalable system trained on hundreds of thousands of speakers. It's very efficient and has proven better performance than traditional systems like cross-entropy training or triplet noise or tuple-engineered noise. The second network, the voice filter network, is the real focus of this work. And here is the system architecture. There are three inputs during training. The reference audio is the one that we compute the D-vector, and we repeat the D-vector every frame as the input to the LSTM. The noisy audio is the one to be enhanced, and the clean audio is the ground truth to compute the noise function. The voice filter network outputs a mask. Then we multiply the mask with the noisy spectrogram to get the enhanced spectrogram. Here, I will explain some of the design details. First, we concatenate the D-vector with the noisy spectrogram between the convolutional layers and the LSTM layers. This is because convolutional layers are used to capture the context information, but D-vector is already very compact. So there is no need to put it before the convolutional layers. Second, we are doing masking, but that's not the only way to do it. Many people use a regression network to directly output the enhanced spectrogram. We find masking is faster and has better performance, so we are using masking instead of regression in our work. About the noise function, we are computing the L2 reconstruction noise for both the magnitude and the complex spectrum. This is following the practice of existing previous work. We also know that human hearing is nonlinear, so we use a power law compression of 0.3 to equalize the importance of quiet sounds relative to loud ones. When we reconstruct the enhanced audio, we need full complex spectrogram. For the magnitude, we can use the one we get by masking the input. For the phase component, we directly use the phase of the noisy input without any processing. Here are the topologies of the networks. Our speaker encoder is simply 3 layers of LSTM. Our voice filter has many more layers, including 2-dimensional convolutional layers, LSTM layer, as well as fully collected layers. Next, I will talk about the data. The data requirements for speaker encoder and the voice filter are very different, so we train them separately. For the speaker encoder, we need a very large number of speakers for training, such that we can generalize well to unseen speakers. Our datasets consist of 34 million utterances from more than 100,000 speakers, but we don't need any transcription of the data. The data requirement for the voice filter network is a bit different. For example, if we want to evaluate the speech recognition performance, then we will need the transcriptions. There are some good public datasets, like the Chime Challenge dataset, but remember, voice filter is a reference audio for enrollment, so we cannot directly use Chime. Instead, we use VCTK and Interspeech in this work. We mentioned that our training workflow needs 3 audios: the clean, noisy, and the reference audio. We can get them all from a clean dataset. So here is the data processing workflow. From the clean dataset, we extract 3 audios. The reference and the clean audios are from the same speaker, and there is an interference audio, which is from a different speaker. We sum the signals from the clean and interference audios to generate the noisy audio for training. Next, I will talk about some of our experimental results. We are going to use 2 metrics, word error rate and source-to-distortion ratio. We report word error rate because our ultimate goal is to improve speech recognition. Our success criterion has 2 parts. First, if the audio is noisy from multiple speakers, voice filter should reduce word error rate, meaning we are really being helpful. Second, if the audio is already very clean from a single speaker, then voice filter should have the same word error rate, meaning we are being harmless. Source to distortion ratio is about the quality of the enhanced audio. It's a popular metric in source separation, so we also use that. For the word error rate, we are going to look at 4 numbers for each experiment. The clean word error rate with and without voice filter, and the noisy word error rate with and without voice filter. We hope that after we use the voice filter, clean word error rate is the same, and the noisy word error rate is lower. In our first experiment, we use Interspeech as our training and evaluation dataset, but try different network topologies. Our experiments show that bidirectional LSTM has the best performance compared with unidirectional LSTM or non-recurrent networks. On clean speech, the word error rate is 11.1, which is very close to when there is no voice filter, which is 10.9. On noisy speech, it reduces word error rate from 55.9 to 23.4, which is a huge improvement. We also try to fix the network topology and use different training data. We found that even if we evaluate on VCTK, we have better performance when we train on Interspeech instead of VCTK. So this is very interesting. This is because VCTK has too few numbers of speakers, only 99, while Interspeech has more than 2,000. So the size of the dataset really matters a lot. Here we also report the source to distortion ratio on our Interspeech experiments. With the bidirectional LSTM, we can see that the median SDR is much larger than without voice filter. Specifically, the last row is the experiment of using the permutation invariant training. Our voice filter has even better performance than this approach. Some of you may question that why the mean source to distortion ratio is so high even without voice filter. This is because when we add speech noise to the clean audio, the speech noise might be extracted from the silent part of the interference audio, ending up with some noisy audios are not noisy at all. But the clean and interference audios are actually of the same volume in our experiments. So for example, when we noisify a clean audio, the clean audio is 10 seconds, and the interference is just 1 second. It ends up that for the final noisy audio, only 1 second of that is noisy, and 9 seconds is very clean. So when we compute the SDR statistically, we get a super high number. Some of them are super high, and the mean is 10. But if you only look at the noisy part, the actual SDR of the noisy part is actually 0. Finally, conclusions and future work. The contributions of this paper include we propose this speaker conditioned voice separation framework named VoiceFilter. We demonstrated that our system has significant word error rate improvements for multi-speaker scenarios and minimal degradation in single-speaker scenarios. It also has better source-to-distortion ratio than conventional permutation invariant training, and the performance could be further improved by using more data. Some of the future work directions. For the long term, we want to build a model that is tiny and performs online inference to make it more portable. We want the model to do speech separation and denoising at the same time to make it more useful and powerful. We also want to train the model jointly with ASR, which should give us even better performance. And here, I want to show a video demo of our very, very early prototype. First, I'm running ASR without a voice filter.
6 foods, cashmere peas, 5 slabs of blue cheese, and maybe a snack from bowl.
I was actually asking what's the weather tomorrow, but there is a background speech, so the recognition is totally wrong. And next, I'm going to enroll my voice on the mobile phone to compute my personal voice profile.
This is Chen speaking. This is Chen running the enrollment. Please remember my voice. What is the time? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is me speaking again. Please remember my voice.
Okay, so at this point, I have enrolled my voice on the mobile phone. And the next thing I'm going to do is that I'm going to run ASR again, but this time I will enable VoiceFilter.
What's the weather tomorrow? What's the weather tomorrow? What's the weather tomorrow?
You can see that I'm asking the same question, and the background speech is also the same, but the recognition is now correct with VoiceFilter. Okay, if you want to learn more about this work or listen to more samples, you can check this website on GitHub. I'm going to show how this website looks like. And the link doesn't work. So let me know if you have any questions.
Okay, let's continue. So the floor is up for questions. I see Mark is having a question there. Thank you for the talk. I just want to give a small comment. So we did very similar thing 2 years ago already, and we have an implementation. So I would have really appreciated that you refer that in the presentation. The method is called SpeakerB. The principle is the architecture is quite similar, but of course we don't use exactly the same thing. But anyway, very nice inclusive demonstration.
Yeah, I'm glad that many people and many different teams are working on this. Like, this is a big problem for speech recognition, and if we can solve this together, like, we are going to have much better speech recognition quality in future products. Thank you.
Okay, more questions?
Thank you for the talk. About the slide 16, you had the cost function.
There's some lag of the computer. I pressed many times. I don't know where it takes to go to. This one?
Yeah.
Yeah.
Could you explain a bit what is combined with what?
Oh, sure. So this as clean and as enhanced. These are the time frequency spectrogram you get from short-term Fourier transform and the indicator. And for the first half and the second half. The second half, so the first half is, you see that I have like a absolute value. That means I take the magnitude of the spectrogram. And the second one, I didn't have the magnitude. It's just the complex value. And for both of them, we have the L2 norm. The first part is the L2 norm of the difference of the magnitude. The second part is the L2 norm of the difference of the complex thing. And there is a 0.3, that's something we call power law compression. That's because in the spectrogram, you can see that there are some very big numbers at high frequency and smaller numbers at low frequency. So we use 0.3 to compress it. Is that clear?
Thank you.
Thank you. I have a question regarding the reference audio. I guess the performance depends on the reference audio from which you extract the vectors, right?
Yes.
So
exactly.
have you done experiments with noisy reference audio?
So when you train the network, you can definitely add some noise to the reference audio. For this group, we are not doing it, but it's pretty doable and it's very easy to implement. And also, we can assume that, like, for example, when you use a device, and the device have a window asking you to register your voice on the device, you are going to, intuitively, you are going to hide yourself in a private room to do that, instead of doing it on the street, right?
Okay, we can take one last final question.
The result you presented on ASR is surprising. Almost all speech enhancement algorithms base ASR, and including Google literature refer to that. Don't use speech enhancement as a prior function for ASR. But for your results, you are getting 11%, which is pretty close to your theme. Have you retrained your ASR with this enhancer?
No, we are using a fixed frozen ASR network.
Okay, thank you very much. Let's thank the speaker.